Welcome to the next session of the subject Engineering Maths. We were in chapter 3, that is the differential calculus major part, and the part of it is differential calculus. Now in this session we discuss series expansions of functions of single variable in terms of Taylor series and Maclaurin series, and followed by classroom workbook. Okay. Now let us see what is a Taylor series. Suppose we have a function f of x which is continuously differentiable in a domain D, which is continuously differentiable in a domain D. Here domain means it is a set. Domain means it is a set. So it may have exactly one element or two elements or infinitely many elements. And A is any element of D. Then this f of x can be represented like this. F of x equal to f of a plus x minus a whole power 1 by 1 factorial into f dash of a plus x minus a whole square divided by 2 factorial into f double dash a plus and so on. I will write nth term. This is x minus a whole power n by n factorial into nth derivative of f at a plus and so on. And this is called the Taylor series expansion of f of x about x equal to a. This is called the Taylor series expansion of f of x about x equal to a. See, in a series expansion we have infinitely many terms. Now let me explain very clearly what we mean by continuously differentiable. This is very important for us. Continuously differentiable means the function has the derivatives of all orders at all points of D. See, suppose if D contains two elements. Suppose D is a set having two elements, for example 1, 2. Now continuously differentiable in this domain means you calculate f dash of 1, first order derivative of f at a point of D. You calculate f double dash of 1, calculate f triple dash of 1, and so on. So all these values are finite values. First order derivative of f at 1, second order derivative, third order derivative, fourth order, fifth order, continuously you will get derivatives of all orders at all points of D. So if I take a equal to 1, I must know what is this. See, I wrote here f dash of a, second derivative, third derivative like this. Whenever this is a finite number, then I can write. So this must be finite number. Next, this must be finite number like this. Therefore, the function has the derivatives of all orders at all points of D. Out of all those points, I am selecting one element which I call it as a. So therefore, whenever f of x is a function which is continuously differentiable in a domain D and a is any element of D, then f of x can be represented like this. F of x is f of a plus x minus a whole power 1 by 1 factorial plus into f dash of a. 1 factorial. Second order derivative and power 2 factorial. Nth order derivative power n factorial, and so on. Therefore, when you replace a by 1, I will get one series expansion. When I take a value 2, I will get different series expansion. That's why this terminology is very important for me. So this is called the Taylor series expansion of f of x about x equal to a. I will tell you the importance of this. Generally, when you go for complex systems, so when you try to find complex integrals, these series expansions are very powerful. Okay, so during complex variables lecture, you can understand very easily what is the advantage of writing a series expansion of f of x about one particular point. So we discussed those points during the chapter complex variables. Okay, but try to understand this. This is called the Taylor series expansion of f of x about x equal to a. Suppose if D has 10 values, then one function will have 10 different series expansions over the set D. So therefore, whenever I have different elements in D, I can get different series expansions for the same function. Okay, so note this point. Let f of x be a function. Let f of x be a function which is continuously differentiable in a domain D. Let f of x be a function which is continuously differentiable in a domain D, and small a be any element of D. Let f of x be a function which is continuously differentiable in a domain D, and small a be any element of D. Then f of x can be represented as f of x equal to write this series expansion f of a plus x minus a whole power 1 by 1 factorial into f dash a plus x minus a whole square by 2 factorial into f double dash a plus and so on, plus x minus a whole power n by n factorial into nth derivative of f at a plus and so on. And this is called the Taylor series expansion of f of x about x equal to a. And this is called the Taylor series expansion of f of x about x equal to a. Now let us see the coefficient of x minus a whole power n in this case. One important concept is coefficient of x minus a whole power n. So here, what is coefficient of x minus a whole power n? This term, nth derivative of f at a divided by n factorial. This is f power n of a divided by n factorial. This is one useful factor for us. Note this point. Coefficient of x minus a whole power n is f power n of a divided by n factorial. Coefficient of x minus a whole power n is f power n of a by n factorial. Next concept, Maclaurin series. Maclaurin series. Now this is a Taylor series expansion of f of x about x equal to a. Now I will take Taylor series expansion of f of x about x equal to 0. So that means in place of a we were taking 0. Of course 0 must be an element of D. Actually in case of Taylor series this a can be any element of D. But in case of Maclaurin series particularly I will replace a by 0. Here x equal to 0 means x value is non-zero. We were expanding series about x equal to 0. That means this is the Taylor series expansion of f of x about x equal to a. Now take x value 0. That means x value is not 0. A value is 0. We were discussing Taylor series expansion about x equal to 0. Got it? So that means a is replacing by 0. Therefore, let us see how this series expansion becomes. This series expansion becomes like this. F of x equal to, replace a by 0. We get f of 0 plus x power 1 by 1 factorial into f dash of 0 plus x square by 2 factorial into f double dash 0 plus and so on, plus x power n by n factorial into nth derivative of f at 0 plus and so on. Therefore, this is called Maclaurin series expansion of the function f of x. So how to define this? The Taylor series expansion of f of x about x equal to 0. The Taylor series expansion of f of x about x equal to 0 is called a Maclaurin series expansion of f of x. Note this point. The Taylor series expansion of f of x. The Taylor series expansion of f of x about x equal to 0. The Taylor series expansion of f of x about x equal to 0 is called a Maclaurin series expansion of f of x. Is called a Maclaurin series expansion of f of x. Therefore, f of x equal to this. f of x equal to this expansion. Write this. Now let us discuss Maclaurin series expansion of three basic functions. So examples. First one is f of x equal to e power x. Now let us find its series expansion. Taylor's Maclaurin series expansion. For the Maclaurin series expansion, I must know its derivatives of all orders when x is replaced by 0. Here f dash of x is e power x. Second derivative is e power x. So like this, when you discuss its nth order derivative, it is again e power x. So replace x by 0. So nth derivative of f at 0 is e power 0. This is 1 only. Therefore, what is my series expansion? F of x equal to f of 0 plus x power 1 by 1 factorial into f dash of 0 plus x square by 2 factorial into f double dash 0 plus and so on. Now what is f of 0? Here f of 0 equal to 1. What is f of x? E power x. Therefore e power x equal to f of 0 is 1 plus 1 plus x power 1 by 1 factorial plus this is x square by 2 factorial because this quantity is 0 1. Next third derivative is 1. So plus x cube by 3 factorial plus and so on. Therefore, this is the Maclaurin series expansion of e power x. Powers of x are in increasing order. All values are having positive sign plus plus plus. Okay, not this. In the previous case, all derivatives are e power x. Therefore, our job is very simple. But in this case, the derivatives will be cos sign like that with alternatively plus and minus symbols. F of x is sin x. Let me write at least some 4 to 5 derivatives. F dash of x is cos x. Second derivative is minus sin x. Third derivative is minus cos x. Fourth derivative is cos x derivative minus sin x. Already we have minus. So this is sin x. Now fifth order derivative, this is cos x. But we need to replace x by 0. Here what is f of 0? This is 0. F dash of 0, cos 0 is 1. This is 0. And this value is minus 1. This is 0. And this value is 1. So we have replaced the x by 0. Therefore this sin x is, because f of x is sin x, f of 0 0, f dash of 0 is 1. So x, but second derivative will be 0. F of 0 0, second derivative is 0, fourth derivative is 0, sixth derivative is 0. First derivative is plus 1, third derivative minus 1, next one. So 1 minus 1 1, plus 1 minus 1 plus 1. That means even derivatives of sine is again sine. When you replace x by 0, it gives 0. Odd derivatives of sine gives either cos x or minus cos x. So you will get either plus 1 or minus 1. Therefore, this is sin x equal to x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial plus and so on. Therefore, it contains only odd powers of x. Only odd powers of x with plus or minus sign alternatively. with plus and minus alternatively. So therefore, because of this reason, we say sin x is odd function. Okay, so work out this. Now we discuss cos function. Example 3, f of x equal to cos x. Now let us find its derivative up to fifth order. Cos x derivative is minus sin x. Its derivative minus cos x, sin x, cos x, and this is minus sin x. Now replace x by 0. This quantity is 1. This will be 0. This will be minus 1. This will be 0. It is plus 1. It is 0. Now you can see alternatively we are getting these values 1 0, minus 1 0, 1 0, again minus 1 0, like this. That means all even derivatives are coming. So f of 0, cos 0 is 1. So second order derivative is minus 1. Fourth order derivative, because when you differentiate cos function, odd number of times sin function will come. Sin 0 is 0. Therefore, in this case, when you are trying to find series expansion of cos x, you don't find odd powers of x. Instead of that, you will get even powers of x, that too alternatively plus and minus symbols. So here what is f of x? This is cos x equal to f of 0. Cos 0 is 1. So minus, here first derivative is 0, but second derivative minus sign will come. So minus x square by 2 factorial. Fourth derivative will come with a plus sign. So 1 minus x square by 2 factorial plus x power 4 by 4 minus x power 6 by 6 factorial plus and so on. So in this case, it has only even powers of x. Only even powers of x with alternatively plus and minus symbols. With alternatively plus and minus signs. So that's why it is also called as an even function. Because of only even powers of x, it has been named as even function. This is an even function. Note these points. Now let us start the classroom workbook based on the concepts maxima and minima of functions of two variables and Taylor series and Maclaurin series. Just all of you go through classroom workbook. Let us start with the question number 38. Question number 38. For the function f of x comma y equal to x square minus y square defined on R square, the point 0 comma 0 is option A, a local minimum, B, neither a local minimum nor a local maximum, C, a local maximum, D, both a local minimum and a local maximum. So I told you many times, so treat function as a classroom. Point is a roll number of the class. So here they were asking what is the status of the roll number 00 inside this class. Suppose when you assign 00, when you treat 00 as a roll number of a student, so what is the status of that particular fellow inside that class? That means whether the student is a least topper of the class or highest topper or none or both. Now let us see. Here directly 00 is given, but make sure that 00 is a stationary point. So you must calculate stationary points at first. Dou f by dou x is 0. This implies dou f by dou x is 2x equal to 2x. This is 0 implies x is a 0. Next to dou f by dou y is minus 2y. So here minus 2y equal to 0 implies y is a 0. So what is my stationary point? 0 comma 0. This is clear. Now we need to calculate d value. D of x comma y equal to fxx into fxy minus fxy whole square. So what is fxx? Dou square f by dou x square. So differentiate this again with respect to x. This becomes 2. F by y. This is dou square f by dou y square. Now differentiate this again with respect to y, we get minus 2. What is fxy? Fxy means dou square f by dou x dou y. So this is nothing but dou by dou x of dou f by dou y. So this is dou by dou x of, here dou f by dou y is minus 2y. Now here we are doing derivative with respect to x, but there are no x terms. Therefore this is 0. Therefore here d of x comma y is fxx into fyy minus fxy whole square. Fxx is 2, fyy is minus 2, fxy is 0. So here d value is minus 4, it is negative. When d value is negative at a stationary point, then the point is neither a local minimum nor a local maximum by second order derivative test. Therefore 0 comma 0 is neither a local minimum nor a local maximum. Neither a local minimum nor a local maximum. Therefore option B is right answer. So this is by using second derivative test. Even this function is a very simple function to manipulate. Now what I will do is, here the domain of the function is r square. I am trying to solve this in a different way. By second order derivative test, we got the conclusion that this is neither a local minimum nor a local maximum. So option B is right answer. Now what I do is, I will try to solve this in the different way. See, suppose I may ask you, what is the status of roll number 15? Suppose in your class, for example. That means whether the student is local minimum or that is least topper or highest topper or both or none. Then suppose if the roll number 15 says to me, sir, my marks are 38. Then I will ask one of the another student in the class, what is your marks? He or she may say that 38. Some student may say that, for example, 47. So suppose if the marks are like this, then how to approach the values? Suppose there is one student in the class whose marks are, for example, marks of x is 28. So x is a student roll number. Suppose marks of roll number y is, for example, 38. So marks of roll number z is 17. So therefore this fellow marks is 28, 17, 38. Therefore this fellow is neither a least topper nor highest topper. That means here marks of z is less than marks of x less than marks of y. So there is one student in the class whose marks dominates this fellow. There is one fellow in the class whose marks are less than this fellow. Therefore this fellow is neither a least topper nor highest topper. It doesn't mean that this fellow is highest topper, this fellow is least topper. Okay. Now let us follow this approach to get the result very easily. Let us calculate function value at 0, 0. This is 0. Now this is the domain is r square. I will consider another point f of 1 comma 2. So therefore in this case this is 1 square minus 2 square. It is minus 3 negative. Suppose I will calculate like this, f of 2 comma 1. This is 2 square minus 1 square. This is 3 positive. Now you can see there is one student in the class whose marks are less than this fellow. There is another student in the class whose marks are 3 greater than this fellow. So therefore 0 is neither a local minimum nor a local maximum. See, in order to say that a student is an average student, it is very simple. Suppose my marks are, assume that I am a student, my marks are, for example, 56. In the same class where I am studying, there is another student whose marks are 68. My marks are 56. In the same class where I am studying, there is another student whose marks is 66. So therefore that fellow is greater than myself. Assume that there is another student in the same class where I am studying, but his marks are 46. So there is one student in the class whose marks are less than my mark. In the same class there is another student whose marks are dominating my marks. What does it mean? I am neither least topper nor highest topper. I am an average student. So saying a student is average is very simple when compared to least topper or highest topper. Therefore, according to these cases, I must look for 2 points where 1 point dominates that fellow, where when 1 point lacks that fellow. In that case, the fellow is neither a local minimum nor a local maximum. Not this. What it is, given a function f of x comma y equal to 4x square plus 6y square minus 8x minus 4y minus 8x minus 4y plus 8. 4x square plus 6y square minus 8x minus 4y plus 8. Its optimal values are minimum equal to 10 by 3, maximum equal to 10 by 3, minimum 8 by 3, maximum 8 by 3. So earlier we handled one question in case of functions of single variable. It is similar to like that. Now let us find stationary points at first. Dou f by dou x equal to, this is 8x minus 8. This equal to 0 implies the value of x is 1. Next, dou f by dou y. This is 12y minus 4. Make this equal to 0. You will get y value equal to 1 by 3. So what is my stationary point? 1 comma 1 by 3. Now dou square f by dou x square. This is 8. Dou square f by dou y square. This is 12. Dou square f by dou x dou y. This is nothing but dou by dou x of dou f by dou y. So this is dou by dou x of dou f by dou y is 12y minus 4. Now this is for dou by dou x. So here it is purely a function of y, but we are doing differentiation with respect to x. So its value is 0. Therefore, what is my d of x comma y? fxx into fxy minus fxy whole square. So what is fxx? Dou square f by dou x square. This is 8. fxy, this is fyy. Sorry. fyy is 12 minus 0 square. So this is 96 greater than 0. So here d value is greater than 0. Even dou square f by dou x square is greater than 0. So here I will write d of stationary point is 1 comma 1 by 3. This is greater than 0, and dou square f by dou x square at the stationary point 1 comma 1 by 3 is greater than 0. Implies, according to second derivative test, the point 1 comma 1 by 3 is a local minimum. This is a local minimum. Therefore, minimum value equal to f of 1 comma 1 by 3. So here f of 1 comma 1 by 3 is, so replace x by 1. This is 4 into 1 square plus 6 into 1 by 3 whole square minus 8 into 1 minus 4 into 1 by 3 plus 8. So this is 4 plus 6 by 9. 4 plus 6 by 9 minus 4 by 3 minus 8 plus 8. This will be nullified. So therefore this is 4 plus, cancel out this. This is 2 by 3 minus 4 by 3. So this is 4 minus 2 by 3. So this value equal to 10 by 3. Therefore a minimum value equal to 10 by 3. Minimum value equal to 10 by 3. So option A is right answer. Note this. The function f of x comma y equal to x square y minus 3xy plus 2y plus x. X square y minus 3xy plus 2y plus x has no local extremum, one local maximum but no local minimum. So like this, options are given in terms of local minimum and local maximum. Let us try this. So at first, let us find stationary points and then we try to apply second derivative test. Here stationary points will be obtained by taking two equations, dou f by dou x equal to 0 and dou f by dou y is 0. So dou f by dou x means 2xy minus 3y plus 1 equal to 0. Dou f by dou x, 2xy minus 3y plus 1 is 0. With this you won't get directly the values of x and y. Now let us go for second equation. Dou f by dou y is 0. So this implies x square minus 3x plus 2 equal to 0. Yeah, now it is an equation in single variable. You can easily get the values of x. So this is x minus 1 into x minus 2 equal to 0. So this implies x values are 1 comma 2. Now substitute x value in this, you will get y value. When x is 1, you will get 1 value for y. When x equal to 2, you will get one more value for y. So if x equal to 1 implies, replace x value here. So this is 2y minus 3y plus 1 is 0. So this implies minus y plus 1 is 0, implies y value is 1. So when x is 1, the point is 1, y value is 1. So 1 comma 1 is one stationary point. Now when x is equal to 2, so this equation becomes, replace x by 2. So 4y minus 3y plus 1 is 0. This implies y plus 1 is 0. This implies y equal to minus 1. Therefore, when x is 2, y becomes minus 1. So the second stationary point is 2 minus 1. One point is 1, 1. Second stationary point is 2 comma minus 1. Now let us see whether it is an extremum point or not, or whether it is an extremum point or not. So let us go for second derivative test. What is fxx? Dou square f by dou x square. So therefore this is dou square f by dou x square. This quantity is, this is dou f by dou x, dou square f by dou x square. This quantity becomes 2y. Fiy is dou square f by dou y square. So therefore this is a purely a function of x. This becomes 0. fxy is dou square f by dou x dou y. This is dou by dou x of dou f by dou y. So this is dou by dou x of dou f by dou y is x square minus 3x plus 2. X square minus 3x plus 2. This is 2x minus 3. Therefore the value of d is fxx into fiy minus fxy whole square. But fxx is 2y. So this is 0. 2y into 0 minus 2x minus 3 whole square. Therefore d value is minus of 2x minus 3 whole square. Now here we have a power 2. So this will be greater than or equal to 0. But when will it be d0? Will d be 0? No chance. D cannot be 0. D will be 0 only when x is 3 by 2. But in the stationary point, one stationary point x value is 2. In another stationary point x value is 1. Therefore d value is negative. D value is negative for 1 comma 1 and 2 comma minus 1. Therefore in both the cases, in this case as well as in this case, the value of d is negative. Therefore no point will be acting as extremum point according to second order derivative test. Therefore it has no local extremum. No local extremum. So option A is right answer. Note this. Yes, question number 41. In the Taylor series expansion of e power x plus sin x about the point x equal to pi, the coefficient of x minus pi whole square. The coefficient of x minus pi whole square is what? So this is my function. What is the function? F of x equal to e power x plus sin x. They were asking coefficient of this. Now it seems to be this is a value and this is n value. A is pi. So here power is 2. So f of x is e power x. Since the power is 2, I must calculate second derivative. What is f dash of x? E power x plus cos x. What is second derivative of this? E power x minus sin x. So here f double dash of pi equal to e power pi minus sin pi, but sin 180 is 0. This is e power pi. Therefore the coefficient of x minus the coefficient of x minus pi whole square equal to second derivative of f at pi divided by 2 factorial. So, but this is actually e power pi. So, this is nothing but e power pi by 2. So, this is 0.5 into e power pi. It's a very straightforward question. Coefficient of x minus a whole power n is nth derivative of f at a divided by n factorial. Here a value is pi, n value is 2. So therefore the required answer is second derivative of f at pi divided by 2 factorial. But what is f of x? E power x plus sin x. So second derivative is e power x minus sin x, replace x by pi. The final value is 0.5 into e power pi. Therefore, option B is right answer for question number 41. Now let us see question number 42. In Taylor series expansion of e power x about x equal to 2, what is coefficient of x minus 2 whole power 4? So we need to find coefficient of x minus 2 whole power 4. Here power is 4. Therefore, this is fourth order derivative of f at 2 divided by 4 factorial. Okay. So therefore, in this case, what is my f of x? E power x. So fourth derivative of f of x is e power x only. Therefore, this value is x is replaced by 2. So therefore, this is e square divided by 4 factorial. So therefore, this is option number C. So just we have applied direct formula, just like previous question. F of x is e power x. We need to find coefficient of x minus 2 whole power 4. So therefore, here a value is 2 and n value is 4. Therefore, the required answer is f power 4 of 2 divided by 4 factorial, because n value is 4, a value 2. So fourth derivative of f is e power x. Replace x by 2. E square divided by 4 factorial. So option C is right answer. 2 e power x plus x square. E power x plus x square, where x is real. Then they asked, choose the Taylor series approximation of f of x around x equal to 0, which includes all powers of x less than or equal to 3. So they were asking Taylor series approximation of f of x equal to this, e power x plus x square, around x equal to 0, which includes all powers less than or equal to 3. So in all options we have terms up to 3. But when you observe all options, 1 plus x is common. 1 plus x is common in all cases. But in case of x square, the coefficients are different. In case of x cube, the coefficients are different. So in case of x cube, in case of first option, x cube coefficient 1. In second case, 1. Third case, 7 by 6. Fourth case, 7. So at first, I will try to find coefficient of x cube. If coefficient of x cube is 7 by 6, C will be right. If it is 7, D will be right. If it is 1, answer can be either A or B. In that case, I need to go for coefficient of x square. So let us go for coefficient of x cube. So this is coefficient of x minus 0 whole cube. So this is divided by third derivative of f at 0 divided by 3 factorial. So I need to go for third derivative. Its first derivative is e power x plus x square into its 1 plus x plus x square derivative 1 plus 2x. Assume that this is x. E power x derivative e power x into its derivative 1 plus 2x. Second derivative. So apply product rule, e power x plus x square into derivative of this 2 plus 1 plus 2x into its derivative is into its derivative is e power x plus x square into 1 plus 2x. So therefore this is 2 into e power x plus x square plus 1 plus 2x whole square into e power x plus x square. So just apply product rule for this. E power x plus x square into derivative of this 2 plus this into derivative of this is this. Now apply third derivative. So therefore this is 2 into e power x plus x square into derivative of this 1 plus 2x. Now product rule here, 1 plus 2x whole square into derivative of this 1 plus 2x into e power x plus x square plus e power x plus x square into derivative of this 2 into 1 plus 2x into 2. Now replace x by 0, f triple dash of 0. This gives 2. This gives 1 plus 2x whole cube 1 and this gives 4. So 2 plus 1 plus 4, this is 7. Therefore this is nothing but 7 by 6. So we have only one option where the coefficient of x cube is 7 by 6. Therefore option C is right answer.